Alright, so in this video we're going to talk about titrations. Now titrations are very important in chemistry. It's an analytical technique that we use a lot, and normally what it's used for is to help determine the concentration of a substance. So you can use it to help you find out how much you had. So in chemistry we like to answer two questions: what is it and how much? Titration is one thing that we utilize to determine how much we have of a substance. So when we talk about neutralization, neutralization is a reaction between an acid and a base. Okay? The products of between an acid and a base are going to be some salt. A salt is any ionic compound, and water. Now, if we have an acid and a base, and we make the salt and the water, okay, let's say that we have a strong acid and a strong base reacting. We're going to create a neutral salt, okay? So strong with a strong, we're going to create neutral substances. Now let's say that I take a weak acid and I react it with a strong base. I actually create a basic salt. Remember, whenever we have an acid and a base, if we're talking about Bronsted Lowry, a weak acid, okay, is going to create a conjugate base. Just like a weak base will create a conjugate acid. So salts, any ionic compound can either be neutral, acidic, or basic. Okay, so when we talk about neutralization reactions, that doesn't always mean that your pH is going to be 7 at the end. So if I have a strong acid and it reacts with a strong base, it'll form neutral substances. Weak acids will react with strong bases to form conjugate bases. So I actually make a basic salt, a basic ionic compound. A weak base reacting with a strong acid is going to form a conjugate acid. So I make something acidic. So my titration, a lot of times will utilize acid and base neutralization reactions. Now you can have other types of reactions with titration, but that's one of the primary reactions that we typically see. So a titration is going to be volumetric analysis. So it's a method in which we have some sort of solution where we know its concentration and we add it into a substance where we don't know the concentration. So we have the unknown substance right here, and then we have the known substance here. And essentially what I do is I put the flask right underneath this burette. Burettes are designed to deliver volume very slowly. So essentially what you're doing is you're going to keep adding a liquid or a solution very, very slowly until the reaction has completed. And then once you look to see how much you've added, you can use that to help you determine how much reacted down here. Okay, so how does a titration work? So you're going to have a substance, a solution, that's in a beaker or a flask. That's called the titrate. The titrate is going to usually have some sort of indicator in it. When we deal with acid-base reactions, we're going to have an indicator that changes colors when the pH changes. Okay? What we do is we're going to react it with another substance in a solution. Okay, this is called the titrant. This is what you're putting in your burette. You're going to slowly add it to the beaker from the burette. So it goes really slow. Okay, you slowly add it until you have completely reacted out the titrate. Okay, so you know that the titrate has completely reacted because you'll have an indicator in there and it will change colors to signify a change in pH. Since we're dealing with acids and bases, once you have taken that titrate and reacted it out completely, you should see a change in pH. So this will be our signal to stop. We stop adding the solution from the burette. Okay, that's called our end point. So the end point is where you end the titration, where the indicator has changed colors. So when we're looking at doing this, okay, we're going to have our titrate in the bottom here. Usually this is going to be the substance where we don't know the concentration. We're going to have another substance that will react with this in the burette, and we're going to slowly add it until we see the indicator change colors. And then what we're going to see is if we have an acid-base reaction, you should see a change in pH. So this is called a titration curve. So, and right here we have phenylalethane. So when you do a titration, you want to go nice and slow, okay? And essentially, the reason you go nice and slow is so that you don't overshoot the point at which you don't want to overshoot the equivalence point. Okay, so the equivalence point is the point at which there are equal amounts of hydronium and hydroxide. Now that's if the ratio is 1:1. Really, the equivalence point is going to be when you have reacted out all of the titrate. So when all the titrate has been reacted out, that is the equivalence point, which for an acid-base reaction, typically what you're going to see is that acid-base reactions are going to be 1:1. So the amount of hydronium and hydroxide will be equal to each other. And if I'm looking at this is the titration curve. This shows me the change in pH as I add my sodium hydroxide here. Well, when I get that dramatic change in pH, okay, in the middle of that point, that is my equivalence point. That's when I've stopped adding my titrant, okay? Okay, the end point and the equivalence point should be the same, but they're not always the same. So the end point is when you stop the titration, okay, which is indicated with a color change or change in pH. The equivalence point is when the titrate has been completely reacted out, okay? Usually, though, you'll see that you go slightly past the equivalence point because that's when the indicator will change colors, when there's a significant change in pH, when it changes a little bit more. So the equivalence point and the end point are not the same thing. We want them to be the same, but they're not the same thing. All right, so the typical type of titration problem is going to be where you have to calculate out a concentration. So it tells me that I have 42.5 milliliters of a 1.3 molar solution of sodium or potassium hydroxide, and that's required to neutralize 50 milliliters of H2SO4. Find the molarity of H2SO4. Okay, so really this is solution stoichiometry. So we are looking for molarity. Molarity is equal to moles over liters of solution. So I'm looking for the molarity of H2SO4. So I would need my moles of H2SO4 and I would need my volume of H2SO4. So let's see what I have. I have a volume and a molarity of hydroxide. I have a volume of the acid, so that's going to be 50 milliliters. So I need the moles. Well, I need the moles of the sulfuric acid. I do have quite a bit of information about a different substance, so this is the stoichiometry part. So let's write out our reaction. So I have H2SO4. Well, it's double replacement. K and H will switch places, so potassium will bond with sulfate. Check your charges. I've got a +1, and this is a -2, so I should have 2 of those. And then for this, I have H, and it's going to switch places with the potassium and become water, HOH. So you can write water as HOH here. It's the same thing. And then I need to balance. So I need 2 and then 2 here. So I know that I have 42.5 milliliters of this, and I know the molarity of this. I also know the volume of this. Now, titration problems, you're going to start where you've got the most information. I've got the most information here. So I have 2 numbers here. I have the volume and I have molarity. Molarity is a conversion factor. You do not start with a molarity. So my volume is 42.5 milliliters, or 0.0425 liters. So now I'm going to go to moles. So I have a volume. Stoichiometry always works the same way. Go to moles of what you have, which is KOH. Then go to moles of what you want. And then go to whatever unit you're looking for. Well, I happen to be looking for moles of sulfuric acid to get my molarity. So I would stop there. So my moles, well, my molarity is 1.3. there's 1.3 moles for every 1 liter of solution. So now I'm going to go to moles of what I want, which is the sulfuric acid. So now moles of KOH, I have 2 of those for every 1 of these. Moles on top of moles, you're looking at the coefficients. All right, so now then when you go through and do the calculation, you're going to get 0.0276 moles, okay? That's not what it's asking for though. We're looking for a molarity. So now we need to take our number of moles and then divide that by 50 milliliters, or 0.05 liters. That's going to give me 0.55 big N. That's my molarity. Okay, so now let's look at a titration curve. So a titration curve looks like this. So you're going to have the pH that's changing as you add the volume of whatever it is that you're adding. Now what you'll notice is that the pH doesn't really change for a while, and then all of a sudden it just shoots up, okay? And it could shoot down too if you were starting with a base. So the portion before the equivalence point, okay, this portion right here where we are not seeing a dramatic change in pH, that's called the buffering region. The equivalence point will be in the middle of this dramatic change. So right here in the middle of this straight line going up is our equivalence point. That is when the amount or the titrate has been completely reacted out. So in this case, our equivalence point has a pH of 7. We've created something that's neutral. Now it keeps going up because I'm continuing to add my base. So of course the pH should go up again. Now, if you have a strong acid with a strong base, this is what your titration curve should look like. Your equivalence point will be at 7 because a strong with a strong will create a neutral salt. If you have a strong acid with a weak base, your equivalence point is going to be slightly below 7. And that's because a conjugate acid is made with a weak base. So I've made something that is acidic. So my dramatic change in pH happens right here. The middle of that is about 6. So my pH is about 6 here. And then if I were to have a weak acid being titrated with a strong base, okay, I'm going to see a pH above 7. And that's because I'm making a conjugate base. So I'm making a basic salt.